In the last video, we had considered symmetric polynomials and Vieta's extension, and this video is like a follow-up to that as we consider Newton's sums for such symmetric polynomials. Let's go ahead and see uh, Newton's sums for polynomials. First of all, Newton's sums provide a structured way to compute power sums of polynomial roots using the coefficients of a polynomial. So you are computing power sums of polynomial roots without having to to get the roots explicitly, just like what we did with Vieta's formula, which could help us get maybe the sum and the basic symmetric sums of a particular polynomial. Okay, so Newton's sums are essential for symmetric polynomials, Vieta's formulas, and even advanced computation problems, like people that go for Olympiads and everything. So Newton's sums are pretty useful in the process of doing all of these things. So look at the setup and definition. Of course, we've seen this a couple of times. Consider a monic polynomial. Of course, a polynomial is monic if the coefficient of the x with the highest exponent is 1, right? So consider a monic polynomial p of x equals x raised power n. Take note that there's no a sub n here. If there would be a sub n at all, it is actually 1. So a sub n x raised power n. So a sub n is 1. Then plus a1 x raised power n minus 1 plus a2 x raised power n minus 2 plus all of that plus. Oh, okay. The an here is the constant actually. So plus an minus 1x plus an. So let the roots of this, of course, because it's a polynomial of degree n, the roots will be n too. So let the roots be r1, r2 up to rn. We define the power sums. Sk equals r1 raised power k plus r2 raised power k plus all of that up to rn raised power k. So Newton's sums give recursive formulas relating sk to the coefficients of a1. So the Newton sums are actually the sums of these powers raised to power k. So, I mean, the power, we'll find out what this is as we go on. So talking about Newton's sums formula now. So for a monic polynomial, like we have said already, for k greater than or equal to 1, so if you have k equals 1, that is the k is actually raised to power 1. I want to believe that is multiplicity in a way. I'm not too sure. Oh, okay. Yeah, maybe it's not multiplicity. So for k greater than or equal to 1 now, we have sk plus a1 sk minus 1 plus a2 sk minus 2 plus all of this up to ak minus 1 s1 plus kak equals 0. So this is the Newton sum formula. So with this, we can do whatever we need to do. So all you just need to do is to establish the value of k. Once you know k is greater than or equal to 1, then let's say k is 2, for instance. So you're going to have s2 plus a1 S1, all right, plus A2 S0, and so on and so forth. So when k is greater than n, that is k is greater than the degree. So you have to continue the same pattern, but coefficients ak with k greater than n are taken as 0. Okay, so let's look at a step-by-step strategy for working this out. So to compute S sub k, first of all, write the Newton relation for k. All right, write the Newton relation, then substitute all known coefficients from the polynomial, then use previously computed S1, S2, and so on, and solve the resulting equation for S sub k, as we're going to see in the next couple of examples. So, what examples? Example one in the quadratic sense, now, which is usually the easiest, right? So consider p of x is x squared minus 5x plus 6. This is about the most common expression we have come across in this whole playlist. So roots are unknown. Look, I mean, we can easily know the roots of these expressions for sure. It's easily x minus 2x minus 3. But let's assume that you don't know the roots. But then sk can be computed even without you knowing the roots. So in this case, now you take a note of the coefficients. A1 is minus 5 and A2 is 6. So by knowing these two alone, then you can continue with other things. You can compute S1, for instance. So to compute S1, Newton's sum for k equals 1 now. Okay, now this is k. So Newton's sum for k equals 1 will now be, because we are looking for sk, so S1 is, so here k is 1. So that means you have, so since k is equal to 1 now, this is what you're going to have. So you have S1, then there's no other S you can get in the game because there's nothing like S naught. So it's just S1, and then the other thing you're going to have will be 1 times A1. All right. So that'll be S1 plus A1. Simply, that's what this is about here. So you just have, going by the expansion, you have S1 plus A1, which is equal to 0. And then you can substitute. You already know A1 to be minus 5. So you have S1 minus 5 equals 0. So S1 is computed to be 5. That's the Newton's sum for that, for K equals 1. So if you go for S equals 2 now, so for S equals 2, Newton's sum for K equals 2 now. So to compute S equals S2 rather, so that means K is equal to 2. And since K is equal to 2, I think you keep referring to this expression. So you have S2 plus A1 S1. Of course, you can't have S0. Then you jump to 2A2, right? You jump to 2A2. So you have S2, A1, S1, then plus 2A2. And that is exactly what we have here. So you have to keep remembering that expression. Okay, let me look at it once more and probably have it up my brain. Oh, yeah, I think it's easy to follow even. SK plus A1, SK minus 1, plus A2, SK minus 2, and so on and so forth until you get to the next will be A3, SK minus 3, all the way down to AK minus 1, S1 plus KAK, and that is equal to 0. Okay, so here now we have Newton's sums for K equals 2, right? So S2 is now A1 S1 plus 2A2 equals 0. Then you substitute now. So S2 is what we are looking for now. Then A1 S1. A1 is minus 5, like we already know. And then S1 is 5 as computed. And then 2A2, that's 2 times 6, because A2 is actually 6. So, and you tidy all of that up. So you have S2 minus 25 plus 12. That's S2 minus 13. So S2 is 13. So, and with all of that done, we then say thus sum of roots. I mean, we can't look for S3 because what we have usually, I think we shouldn't go beyond the degree n, because like we have here already. So when K is greater than n, continue the same pattern, but coefficients AK with K greater than n are taken as 0. So, and since the coefficient is already 0, so there's no point going beyond the degree of the polynomial I want to believe. Yeah, we'll see a cubic one now. So for cubic, we go 3. So here we have S1 to be 5 and S2 is 13. Okay. So in example 2 now, which is cubic again, which is now cubic rather, consider P of x equals x cubed minus 3x squared plus 4x minus 2. So here A1 is minus 3, A2 is 4, A3 is minus 2. So to compute S1, we just know that's S1 plus A1, which is 0. Then we have S1 minus 3 equals 0. And I mean, A1 is minus 3, right? So we just put the A1 here, minus 3. So S1 is 3. Then we go for S2. To do S2, that will be S2 A1 S1 plus 2A2, and that is equal to 0. Okay, and that'll be S2 we don't know. Then A1 we know to be minus 3. S1 we know to be 3. So that's minus 3 into 3 plus 2 times A2. A2 is A2 is 4 rather. So we have S2 minus 9 plus 8. That's S2 minus 1 equals 0. So that means S2 is 1. So S1 is 3, S2 is 1. Then we can go for S3 again. For S3, that'll be S3, A1, S2, A2, S2 plus 3A3, right? So now I think you can see a pattern already. For S1, we have two terms. So that's S1 plus A1. For S2, we have three terms. Starting from S2, so S2, A1, S1, then 2A2. So everything will end with that 2 and A2, like that. So KAK. Then for S3 now, you're going to have three terms plus 3A3. Okay? And what are the three terms? You have S3 plus A1 S2 plus A2 S1 plus 3A3 equals 0. So that means S3 minus A1. A1 again, we know it to be minus 3. So we have minus 3 into S2, which we found to be 1. Then A2 S1. So A2 again is 4. S1 we know is 1. So that's 4 times 3. Then 3A3, that's 3 into A3 is minus 2. Okay, so we have once you have exhausted all those things up there, you don't need more terms. So S minus 3 plus 12 minus 6. That's minus 3 in short. This whole thing will be minus 3. Yeah, no. Minus 3 minus 6, that's minus 9. Minus 9 plus 12, that's plus 3. Sorry, S3 plus 3 equals 0. That means S3 is minus 3. So the interpretation of this simply means that from the cubic example, S1 is 3, S2 is 1, and S3 is minus 3. So this simply means that R1 plus R2 plus R3 is 3. Then R1 squared plus R2 squared plus R3 squared is also is 1. Then for S3 now, S3 is R1 cube plus R2 cube plus R3 cube is minus 3. That's what this whole thing is. So you obtain this without solving. So without solving the cubic expression, we get this particular result. In the case of the sum, okay, sum of roots now. Sum of roots simply means actually this is for the sum of roots. I think I want to see to that to make it as clear as possible. Okay, where is it now? So sum of roots, we are saying that R1 plus R2 is equal to, so I mean we have the dollar sign here, is equal to 5. Then square of roots, sum of squares of roots now. That'll be R underscore 1 raised to power 2 plus R2 R2 rather raised to power 2 is equal to 13. That's what this is simply talking about here, as you can see. So we are saying that oh, this is sum of roots. This should be plus, sorry. So what we are simply saying is that, of course, thankfully we know the roots of x squared minus 5x plus 6. That'll be 2 and 3. So 2 plus 3 is 5. Then 2 squared is 4. 3 squared is 9. 4 plus 9 is 13. So that's what this whole Newton sum of polynomials, uh, Newton sums for polynomials is about. Okay. Uh, let's see. So sometimes you may not even be able to find the solutions, but you can definitely find the sum of the roots, the Newton sums of the roots. So here you have the root directly added together, you have 3. Then the roots directly, if you square each root and add together, you get 1. And then you have this whole thing again, R1 cube plus R2 cube plus all this. So you obtain this without solving. So example 3 now, for quartic now we have k greater than n. Okay. So for k greater than n, we have 1, 2, 3, 4. Okay. So we have x raised to power 4, 2x cubed minus x squared plus 5x minus 7. So first of all, we compute S1. So S1 plus A1 is 0. Then that means S1 plus 2 is equal to 0. That means S1 is minus 2. Next, we have S2 plus A1 S1 plus 2A2 equals 0. So that's S2 plus 2 into minus 2. That's S1 now plus 2 into A2, that's minus 1. So that'll be S minus 2 minus 4 minus 2 equals 0. That's S2 equals 6. Next, we have S3 is A1 S2 plus A2 S1 plus 3A3 equals 0. Okay, everything always ends with S1. Okay, then before you have the KAK, right? So again, you have S3 into 2 times 6 plus minus 1 into S1. So A2 is minus 1, S1 is minus 2, then plus 3 times 5, A3 is 5. So we have 3A3. So we have 2 times 6, 12, minus 1 times 2, that's 2. Minus 1 times minus 2, that's 2. 3 times 5 is 15. So we have 29. S3 plus 29 is 0. So S3 is minus 29. And then here, we now want to compute S5. That's the first example with k greater than n. So for k equals 5 now, we have S5 plus A1 S4 plus A2 S3 plus A3 S2 plus A4 S1 equals 0. But of course, we can't compute for k is 5 if we don't know k is 4. So for k4, right, we then have, so for k4, for k equals 4, we have S4 plus A1 S3 plus A2 S2 plus A3 S1 plus 4A4. 4A4. Here we don't have A5. We don't have A5. So if you are going for, so anywhere where you should have had A5 is will be thrown away. So But for this one, now, if you substitute the known values, you get S4 to be 102. So if you now plug this into S5 relation, so that means, okay, now I get it. So if we need, so it means we can actually have n k greater than n, in the sense that, even this one that has order. Okay, I mean, let me finish up with this so I stop jumping all over the place. Okay, so now if you plug this into S5 relation, you have S5 to be minus 27. So a very good example of this for order 2 that we did initially, which, I mean, it's easier to understand things with order 2 because the order is very small. So here we know that R1 is 2 and R2 is 3, for instance. So imagine that we now need, we didn't go for R. So if you want R cube plus R1 cube plus R2 cube, that's where the challenge is. That's S3 now. So in that case, for the S3, so we now have to say where we should have KAK, that will now be missing. So we have to stop a step short of that because that is not available. So any coefficient that you don't have, you don't represent it. So normally here this should end with 5A5, but from what we have listed, there's no A5 here. We have A4. So that's why we don't go that far. But it doesn't mean that you cannot compute the fifth, the R raised to power 5, R1 raised to power 5 plus R2 raised to power 5 up to R5 raised to power 5. That, I mean, for a quartic, it should be R1, R2, R3, R4. So we can, in as much as we don't have A5, you can still go ahead and do R1 raised to power 5, plus R2 raised to power 5 plus R3 raised to power 5 plus R4 raised to power 5 plus R5 raised plus, yeah, plus R4 raised to power 5. Like that, we can still do that. So, but if you do that here, S5 is going to give us minus 277. But of course, when I get to the practice questions, I'm going to look for a case like that and see how we can even go beyond what is necessary. Okay, so we have now, in the summary table, for a monic polynomial, when k is 1, the Newton sum relation will be S1 plus A1 equals 0. Then when k is 2, of course, we have S2, A1, S1 plus 2A2 equals 0. When it is 3, so for 1, you have 2 terms equals 0. For 2, you have 3 terms equals 0. For 3, you have 4 terms equals 0. And that's the pattern. It starts from S3 plus A1, S2 plus A2, S1 plus 3A3 equals 0. Then for 4, you have 5 terms, and that's 0. So that's S4 plus A1, S3 plus A2, S2 plus A3, S1. Then you go ahead and have 4A4, and that's 0. So general K, you have SK plus A1, SK minus 1 plus A2, SK minus 2 plus all that up to AK minus 1, S1 plus KAK, and that is equal to 0. Okay. Now we come to the practice questions where I think I'll take one or two questions. I think one question should suffice. So let me take one question. So these are the 10 questions you want to try your hands on. Well, I'm going to solve maybe one of it before we go. Then I also like to practicalize the let me see if all the roots are available. So I'll try the first one. That's x cubed minus 2x squared plus 5x minus 7. So if all the three roots are real, then it will be easy for me to test my results at the end of the day. So I have x raised to power 3 minus 2x raised to power 2 plus 5x minus 7. Oh, okay. Not all. So only one root is available. The others are possibly complex. But it doesn't mean that you cannot do whatever you have to do with it. So let's see, which one can I try now? Okay. I mean, I think there's this expansion that we know all the roots. So maybe I can work with that. Okay. I'll quickly check that in one of the last videos I did. Talk under downloads now, yeah, here. So I'll just quickly go for that and check. The last video I made, it was symmetric polynomials. So I think one of those polynomials is pretty popular. So let me just work with that. And since we know the roots to be 1, 2, 3, that can be really helpful. Okay, I think it was question 1 here. Yes, this one now. At least we are sure the roots are 1, 2, and 3. So it's easy to work with. So we have x cubed plus 4x squared plus 5x. No, it can't be this. It's not this. It's not this. It's I think it's another one. I'll identify it once I see it. Yes, this x cubed minus 6x squared plus 11x minus 6. Yeah. So this is more like it. So we know the roots are 1, 2, and 3. So we can easily play with this. So now, so I'm not taking any of this, but take notes. Oh, okay, it's even here. It's in question 4. Sorry. Yeah. Okay, we want to compute S4. Ah, nice, nice. It's here. Okay. And the reason why I'm picking it, so I'm solving question 6. I didn't take notes, it was there. So I'm picking question 6 because all the roots are known. So that's x cubed minus 6x squared plus 11x minus 6, and we see all the three roots are known: 1, 2, and 3. So we can verify whatever we are doing using the Newton's sum. Okay, so I come to the worksheet now. So we want to compute S4 for x raised to power 3 minus 6x squared plus 11x minus 6 equals 0. Okay, from what we know, before we can compute S4, okay, well, since it is S4 we want to compute, right? To compute S4, we know already that S4 should be A1. How does it start now? I think it starts with just S3. Let me confirm that. Okay, so it starts with S4, then A1, the rest. Okay, I'll go for that now. This. So we have S4 plus A1 S3 plus A2 S plus A2 S2 plus A3 S1 plus A plus K plus 4A4, in short, plus 4A4 equals 0. This is what we need to compute S4. This is what we need to compute S4. So, but I mean, we need to get S1, S2, and all the rest first. So, so we now go one after the other. For S1, we have S1 plus A1 is equal to 0. So before we even begin to do this now, okay, so we say from P of x equals x cubed minus 6x squared plus 11x minus 6, okay, equals 0. We know that A1 is minus 6, that's the coefficient of x squared. A2 is 11, and A3 is minus 6, okay? A3 is equal to minus 6. So we have this. So we have to keep referring to this from time to time. So we can then go for S1. So we have to have S1 plus A1 equals 0. So S1 plus A1 equals 0. That means that S1 plus A1 is minus 6. So that's S1 minus 6 equals 0. That implies that S1 minus 6 is 0. That means that S1 is equal to 6. So we got S1 like that. So that is simply the sum of the roots. And we know the three roots are, so this is simply telling us that S1 is equal to root 1 plus root 2 plus root 3 equals 6. Okay. Of course, the hint, maybe if I want to add a hint here, so I can say hint, roots are 1, 2, and 3. So we can easily verify. So we want 1 plus 2 plus 3 is 6. So we see that that works good. Okay. So the next thing we want to do is S2. So for S2, how do we go? We know we have S2 plus AS1 plus plus 2 A2 equals 0. Okay. So S2 is what we are looking for. So A1, yeah, A1 A1, S1. So what is A1? A1 is minus 6, right? A1 again is minus 6, minus 6. S1 now is the 6 we just got now, plus 2. A2, we go for A2 now. A2 is 11, okay? A2 is 11, and that is equal to 0. So we have S2 minus 36 plus 22 equals 0. So that is S2 minus 14, I believe. Yeah, I think that's correct, equals 0. So S2 now is equal to 14, okay? Can we check? So if we check that, we see that S2 is supposed to be R1 squared plus R2 squared plus R3 squared. Okay, that means we have 1 squared plus 2 squared plus 3 squared. Okay, and that's simply, we already have the hint that the solutions are 1, 2, and 3. So that's 9 plus 4, 13 plus 1, 14. So this is correct. So we can easily check like that. So it's good to work with this so we know what we are actually on course. So that's S2. We are going to S4. In fact, I'll go to S5 so we can see the need for dropping anything that is not available. So for S3 now, for S3, we know S3 plus A1 S2 plus A2 S1 plus, for S3 we need 4 terms. So we have the first 3 terms. 3A3, and that is equal to 0. So we go S3 is what we need, plus A1. We know A1 again. A1 is already minus 6. So we have A1 is minus 6. S2 we just found to be 14. So we found S2 to be 14. A2. A2 is 11. A2 is 11. Okay. A2 is 11 into S1. I think S1 we got that to be 6. S1 is 6, yeah. And then 3, A3. A3 is this coefficient now. So what is A3? A3 is minus 6. Really? A3 is minus 6. X cubed minus 6x squared plus 11x minus 6. Yeah, A3 is minus 6. Okay. So A3 is minus 6. That is equal to 0. So we have S2, 6 times 14. 6 times 4, that's minus in short. 6 times 24 times 4 is 24. That's 84, right? That's 42 times 2, correct. Then plus 66 minus 18 equals 0. Yeah. So that we have minus 84 plus 66. That's, I believe that's minus 20. That's minus 18, right? That should be 18. I think that should be minus 18. So 18, 4. Yeah, that's minus 18. So this should be minus 36 equals 0. Okay? So that means that S2 is equal to 36. Oh, sorry, S3. S3 is 36. S3 is equal to 36. So let's check. Check. We have S3 to be R1 cube plus R2 cube plus R3 cube. That's the same thing as 1 squared, 1 cube plus 2 cube plus 3 cube. Okay, that's 1 plus 8 plus 27. 27 plus 8 is 35. That's 36. Correct. Okay, so we are good. So we need S4. Okay, I think the S4 was intentional. So because we don't have A4 anymore. Okay, so I think I don't have to do S5 because S4 already takes care of what I was worried about. So because it's of degree 3, you can only find all the necessary coefficient for up to S3, but we can still do S4. So we can answer for S4. So again, we know S4 plus A1 S3 plus A2 S2 plus A3 S1 plus 4A4 is equal to 0. Okay, but now we know we only have A1, A2, A3. Okay, we know we have A1, A2, A3. We know A1 is minus 6, A2 is 11, and A3 is minus 6. Okay, A4 of course is 0 because we don't have anything like A4 here. Okay, so it's taken to be 0. So what happens now is this is S4 plus A1 is minus 6, and S3 that we just got up there is 36. So S3 is 36 plus A2, which is 11, S2, S2, we got S2 to be 14. So S2 is 14 plus A3. A3 is minus 6. S1 is 6. Then plus 4. A4 is 0 because there's nothing like A4 in that expression. So we now say this is S4. 36 times 6 should be minus 216. Minus 6 times 36, that's 216. 6 times 6 is 36. We have 3. 18, that, yeah. Then 11 times 14 is 154. Okay. Just have 1. 1 plus 4, 5, then 4. Then minus 36 plus 0. You know, this is gone and this is equal to 0. So we now have S4. So we have to tidy this up now. We have, how do we do this? So minus 216 minus 36. So minus 216 minus 36. This is 2. This is 4. This is 5. That's minus 252. So minus 252, 154 now. So that's definitely going to be S4 minus something. So whatever we get. So that should be S4 minus 12 minus 4. That's 8, right? Then 9 minus 5. I mean, 40 minus 5, that's 9. That's all we get. So this minus 98 equals 0 right here. So even without the A4, we can still go this far. So in this case now, S4 is equal to 98. And that is it. So again, we can check. Okay, so check. So if we check this, we know that S4 is the same thing as R1 squared plus R1 raised to power 4. Okay, R1 raised to power 4 plus R2 raised to power 4 plus R3 raised to power 4. That's what S4 means. So that means S4 is equal to 1 raised to power 4 because we know the roots are this and they are symmetric. 1 raised to power 4 plus 2 raised to power, 1 raised to power 4 plus 2 raised to power 4 plus 3 raised to power 4, like this. So that means S4 is equal to 1 plus 2 raised to power 4 is 2 times, that's 16, then plus 81. Okay, so S4 now is 81 plus 16, that's 97. That is 98. Okay, so everything is making sense. So the answer is 98. So with that, we come to the end of that. So you see, we can find S4. So because of course we know that 4 K is 4, but n is 3. Okay, n is 3. So it's possible to find S4 even when k is greater than n. The only thing is that the only issue is that A4 will be 0. That's all we are saying. Okay, so it's really possible. So I think I made a statement earlier because I was talking about the degree. So you can even look for S10. The only thing is that all the coefficients you need for them won't be available, but you still get the correct answer. Okay. And I mean, checking like this can also help. So, so if you now want to do, okay, I mean, maybe I can even still do a very simple equation we'll be working with. So, we know this, that, imagine, let's compute S3 for, for, um, x squared minus 5x plus 6 equals 0. Okay, let's compute S3 for this. So first of all, we know that we know here that A1 is equal to minus 5 and A2 is equal to 6. So if you are computing S3, we don't have A3. So let's start from the beginning. So we can say, first of all, S1 plus A1 is equal to 0. We did that much the other time. So that's S1 minus 5 is equal to 0. That implies that S1 is equal to 5. So we have this sorted. Then next, we have S2 plus AS1 plus 2A2 equals 0. Okay, so S2 we don't know, plus okay, this is A1, right? A1 is minus 5 like we did before. So that's minus 5. S1 is 5 also, like we got here. Then 2 A2 is 6 equals 0. Okay. Okay, I mean, we can check, right? So to check here, we have, of course, we know the roots here. We know that we have the hint that the roots are 2 and 3. Okay. So since we know that those roots, so we know S1 is R1 plus R2, which is 2 plus 3, and that is 5. So that's excellent. Okay. So here now, back to this, we have S2 minus 25 plus 12 equals 0. So that means S2 minus 13 is equal to 0. Okay, so that means S2 is equal to 13. So now we can check. So we want to check now that S2 is the same thing as R1 squared plus R2 squared. That is 2 squared plus 3 squared. Okay, that is 4 plus 9, which is 13. So that is correct. Then, I mean, we are looking for S3. So we can go for S3. So we know S3 plus A1 S2 plus A2 S1. Okay, plus 3A3 equals 0. Okay, so we know S3. I mean, we don't know S3. We know A1. A1 is minus 5. So A1 is minus 5. We know S2 now. S2 is 13. S2 is 13. A2 is 6, right? A2 is 6. Yeah, this. So A2 is 6. Then S1 is 5, I believe. S1 is 5, the first one we got right there. Then 3A3, that's 3 into 0 because there's no A3. We only have A1 and A2. Okay, so A3 is 0, and all of this now is equal to 0. So we have S3 minus 65 plus 30. This is 0, and this is equal to 0. So we have S3 minus 35 is equal to 0. So that means S3 is equal to 35. Okay, so we can check again. Okay, we're checking. So if we check, we have S3, that should be R1 raised to power 3 plus R2 raised to power 3 plus R4 raised. I mean, I wonder why I'm just in a rush. So S3 is R1 raised to power 3 plus R2 raised to power 3. That means we have 2 raised to power 3, the first root. The second root is 3 raised to power 3. So, I mean, the reason why we say symmetric polynomial here is that if you like, you can R1, if R1 is 3 and R2 is 2, it doesn't change anything. Okay. So here you have 2 raised by 3 is 8, 3 raised by 3 is 27, and that is 8 plus this, that's 35. Okay. So we can keep going. In fact, we can keep going and we'll still get our answers. Okay, maybe I should even push. Let me still go for S4. Okay, like I'm excited right now. So we can still do S4. S4 is okay, that S4 plus A1 S3 plus A2 S2 plus A3, right? A3 S1 plus 1, 2, 3, 4 plus what with A1, A2, A3. So after S1 we just have 4 A4, okay? Equals 0. So then we have S4 now, okay? Plus okay, there's nothing like A3, there's nothing like A4, as we already know. Okay, so I mean, let's just do it. So plus A1, A1 is minus 5, and S3 that we just got is 35. S3 is 35. A2, we know A2 is 6, S2 is 5. I doubt it. I think S2 is 14. S2 should be 4. S2 is 13. Yeah, S2 is 13. A2 is 6, S2 is 13. So A3 is 0, S1, whatever S1 is, it doesn't even matter. So, but we know S1 is 5. Then 4 is 0. I mean, we have 4, okay? 4 into another 0 because the A3 and A2 don't exist. So this can go. I mean, A3 and A4 do not exist. So we have S4 minus 5 times 35. I think it should be 105. 5 times 5 is 25. We have 5. 5 times 3, 15. 5 times 5, 25. Okay. I guess this should be wrong. 5 times 5 is 25. We have 2. 5 times 3 is 15. I think that's 175, I hope. Plus 6 times 3, that's 78. Yeah, 6 times 3, 18. Then, yeah, 78. And that is equal to 0. So that's S4 minus. Okay, 175 minus 78. 78, 75 cancels out. We have 3. So 100, um, that should be 98, I think. Is it 98 or 97? I think it's 97. Yeah, equals 0. Yeah. The happy thing is that we can always check. So S4 is 97. Okay. So we check now. So to check, we know that S4 should be R1 raised to power 4 plus R2 raised to power 4. Easy. So we have S4 to be R1 is 2. So 2 raised to power 4 plus 3 raised to power 4. So S4 is 2 raised to power 4 is 16. 3 raised to power 4 is 81. Excellently, S4 is 97. Okay, so that makes plenty sense. So with that, we come to the end of this interesting video about Newton's sum for polynomials. So this simply tells you that even without solving a polynomial, you can actually find the Newton sum. And the Newton sum simply means like S1. Okay, I think let's establish it again. I mean, I've done this over and over again, but I think I just want to emphasize it that S1 simply means R1 plus R1. Okay, R1 plus okay, let's say for P of K, which is from, say, which has x raised to power n. Okay, x raised to power n plus what we start from a1, right? So we have a1 x raised to power n minus 1. Okay, I mean, I can even just say for a degree n polynomial, let's even leave it like that. For a degree n polynomial, okay, such that p of x is equal to x raised to power n plus a1 x raised to power n minus 1, yeah, plus a2 x raised to power n minus 2 plus all that up to, say, a so that's an minus 1, okay, an minus 1 x an minus 1 uh x, like that, okay, um okay, up to this, right? And then you have an, you have uh n a n, okay, like that. Okay, I mean, let's just forget about this. Like, there's no point stressing about this. I mean, the whole thing is established. All I'm just trying to say is that uh given given uh given let me uh for two roots, right? Okay, we are simply saying that S1 is R1 plus R2, and we're saying S2 is R1 squared plus R2 squared. S3 is R1 cube plus R2 cube. That's when we are dealing with two roots. Now, if it is cubic, now you have to do R1, R2, R3. S4 will simply be R1 raised to power 4 plus R2 raised to power 4. S5 will be R1 raised to power 5 plus R2 raised to power 5. Now you can take all this one all the way down to n. Like Sn will be R1 raised to power n plus R2 raised to power n. That's basically what we are talking about. So that's what I was trying to drive at. Okay. Yeah, so thank you so much for listening to this. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel free to let me know. If you have subscribed already, I thank you very much. If you haven't subscribed, what are you waiting for? Go ahead and subscribe for sure. And hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of the channel, and that comes to some special privileges. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.